Okay, so yeah, during this lecture, model, which is a very vague term, a model can be anything, can be Claudia Schiffer or Johnny Depp. Model can be a car model, but in this lecture, a model means a hypothesis space. So when I say a model, then this could be, for example, the space of all linear functions, or another model is the space of all polynomials with degree, maximum degree 10. Or another model could be all polynomials with degree or maximum degree 15. So this is what I mean by a model in this lecture. Are there any questions at this point? Okay, so all I talked about today is again organized by three components. So what are the three main components of machine learning? Very good. So this should be now really burned into your brains. The three components are data, hypothesis space, and loss. And the focus today is on the second component, hypothesis space. So today we will talk about how we can evaluate the quality of a hypothesis space, which means to validate a hypothesis space or to validate a model, how we can choose between different hypothesis spaces, which is model selection, and how to regularize a model. So how to regularize a big hypothesis space. Okay, so let's start first with data. So what is data? Data, in the most general form, is just a bunch of data points which are similar types of information carrying objects. So this is highly abstract, which makes it very flexible and powerful as a concept. We can model anything as a data point, but we must define it, we must make it concrete. So we must define what are the features, what are the properties that can be measured easily, and what could be labels or higher level facts or quantities of interest that we're interested in the end. So for example, a data point could be some ski day. So there was one question, is there any scenario where features are hard to measure? Well, by definition, features are anything which are easy to measure. Anything which is hard to measure, we could define as a label. And we could develop machine learning methods to predict these hard to measure quantities or labels. So anything that is hard to measure is by definition a label. Okay, so let's say we are somewhere okay, another comment, how do you quantify a label? So you can define the label. You define the label. What labels are and what features are is a design choice. Let's now look at a particular example. So we define now a machine learning problem where a data point is some ski day. So some particular day in the French Alps, for example. And what we can measure easily in the morning is the morning temperature. So we look at the morning temperature, but what we would like to know about this data point, what is the quantity of interest, is the maximum daytime temperature. Why could we be interested in the maximum daytime temperature? Why is this useful to know for a ski day? Any skiers here? Yeah, the clothing. So how much clothes should I put on? If it will be very warm at lunch, plus 5 degrees, then I better not put too much clothes on. Okay, so that's why it might be interesting, or a quantity of interest. Yeah, and in machine learning, we are always interested in having as many of data points as possible. So we want many data points. A data set or data is a bunch of data points. And for some of them, let's say we know what the label is. So we know what the maximum daytime temperature is. How can we know that for data points? How can we get such data points for which we know what the quantity of interest is or was? where can we get labeled data from? From historic data. So we have to look into the past and hope that the behavior or the relation between morning temperature and maximum temperature last week is similar than today. And often this is a reasonable assumption, but sometimes it might not be good. But let's say we have such historic data and it's representative for how the morning temperature is related to the maximum temperature. And the key quantity or a measure of this data set or the training data set is the sample size. So the number of labeled data points. So let's say we have four data points. So for 4 ski days last week, we know what the feature was, so what the morning temperature was, and what then the maximum temperature was, so the label. So the goal now in machine learning is to learn a predictor that reads in the feature for a new data point, like for today in the morning, and gives us a prediction for the maximum daytime temperature. There's one comment or question, does the sample size affect the features? No. So the sample size is one parameter of the data. Another parameter or other quantity that measures data is the number of features. But now we only consider the number of data points. Another comment, does it mean in the end that the label was measured at some point? Yes, so for labeled data, in order to get labeled data, we must have measured the label somehow. Yeah, and this might be non-trivial. So it might be difficult to get a lot of labeled data because, for example, the historic data, when we look into the last week, might not be representative, or only the last 3 days might be representative for today because the general weather condition changes. So it's then basically useless to use a data point for 3 weeks ago. So it's often difficult to get a lot of labeled data. And we like to develop machine learning methods that get by with very little training data. So we would like to have methods that get along with a small m. So in this case, we have 4 labeled data points. Okay, second component. So we want to learn a predictor that reads in the feature, the minimum temperature, like minus 10 degrees, and outputs a prediction for the maximum temperature, like minus 2.3 degrees. How many such predictors are there? If we assume that the features and the label are numeric, modeled as a real number. So how many possible predictor mappings do we have? Infinite, and a lot of infinite, uncountably infinite. So we need to reduce because we only have finite computational resources. So we need to somehow reduce the set of predictors, and that's exactly what a hypothesis space is. So a hypothesis space is a subset of predictors that we can search over easily. For example, one such hypothesis space, which I call model 1, is the space of linear predictors. So this hypothesis space consists of all linear predictors. Okay? But there are other choices. So I could also say, why not using another set of predictor functions, which are degree 3 polynomials. So this model 2 is the hypothesis space that consists of all predictor functions that are in the form of a polynomial with maximum degree 3. Yep. So as you see, by the way, these linear predictors are still there. Is this an error? Did I forget to remove the linear predictors here? Do we have mathematicians in the audience? Are linear predictors also elements of this model 2? So are linear predictors also examples of a degree polynomials with maximum degree 3? Yes, yes, because a polynomial of degree 3, okay, let's try this out. It's a bit clumsy to write here, but let's do it. So a polynomial of degree 3 looks like this. For example, 1 plus x plus some constant or coefficient b, x squared plus some coefficient c, some number, x to the power of 3, where x is the feature. Okay, and if you choose b equal to 0 and c equal to 0, this is a particular example of a degree 3 polynomial or a polynomial with maximum degree 3, then you get a linear function. So all the linear functions that we had before are also element of this model 2. So we have a nested structure. So we have linear predictors. This is the model 1. This is one hypothesis space. And then we have another hypothesis space, which is given by all degree 3 polynomials, which is larger. There's one question. Can we use the combination of linear predictors and polynomial predictors? Yeah, as I said, linear predictors are a special case of polynomial predictors. So if we allow polynomials, then this includes linear predictors as a special case, because we can always set the coefficients of the larger powers of the higher order powers to 0, and we get linear predictors. So these are two different hypothesis spaces. We could also add other hypothesis spaces. We could say, well, we also have a model 3, which are decision trees, or a model 4, which is an artificial neural network. And the question now is how to choose between 3 different models. So, but first, what do we do if we use a particular model? So let's say we use model 1, which are all linear predictors. So how do we find the best linear predictor out of this hypothesis space? And here comes the third component into play of machine learning. Loss function, yes, a loss function. We learn, for example, a linear predictor, so we find the best element of this model 1, or the best linear predictor out of model 1, by minimizing the training error. So let's say we use one particular loss function, the squared error loss. We could also use the Huber loss or the absolute error loss, but let's say for this case we use the squared error loss and minimize it. So does anybody know how to minimize or how to find the linear predictor which has the minimum squared error loss or minimum training error? How did you do it so far in this course? Did you do some derivations, compute the derivative of a loss function? But how did you do it in the coding assignments? By fitting, yeah, there's a function. I think it's called linear regressor dot fit. And when you call this function dot fit, this chooses, what this function does is it goes over all, it searches over this space of linear predictors and chooses the one which has the smallest loss, average loss. So there's no need to derive anything. We have Python functions for this. Okay, and we can do the same with the other model, also with the other hypothesis space. So we learn the best degree 3 polynomial by choosing the coefficients of the polynomial in order to minimize the training error. So what do you guess? If we look at the polynomial with the minimum training error, and if we look at the linear model, which has the minimum training error, what will give a smaller training error? The linear predictor, the best linear predictor, or the best degree 3 polynomial? Yes, the degree 3 polynomial, because a linear predictor is a special case of a degree 3 polynomial. So whatever we can achieve with a linear predictor, for sure we can also achieve by choosing the coefficients suitably of a degree 3 polynomial. So this is almost trivial because the degree 3 polynomials contain as a special case linear predictors. So the training error will always be smaller of a larger hypothesis space. So if we use the training error to choose the hypothesis space, we will always be guided to the largest possible model there is. So, but what is the problem with this approach? Why should we not select a model based on the training error, which would always guide us to the largest possible model? Yeah, one reason could be computational. That it takes longer to find the best degree 3 polynomial than the linear predictor. So at some point, we just don't have the computational power. And there's another reason, overfitting. So let's now discuss overfitting. So if we fit this degree 3 polynomial to our 4 data points, we almost get training error 0. So somehow we managed to almost perfectly fit the training point. But now comes in a new data point like today. Let's say these 4 data points that we used to train the predictor were the previous 4 days, the previous 4 ski days. But there's a new data point today. And if we would use the predictor that we learned from the previous 4 days, we would get the prediction for today plus 40 degrees. And we would go skiing naked. So for this new data point, for today, the prediction of the maximum daytime temperature fails completely. And this is what is called overfitting. So we fit the training data almost perfectly, but we overfit it. We do not really learn the true relation or the intrinsic relation between feature and label, which should be somewhat monotonous. So if the minimum temperature is higher, then also the maximum daytime temperature should be higher, and also in the other direction. So this is a clear case of overfitting, and this is maybe one of the key pitfalls when you start to apply machine learning methods. Because modern machine learning models like deep neural networks, they are so powerful, they are like polynomials with maximum degree 1000. So you can fit any modest sample size almost perfectly. So you will get training error 0, but this doesn't mean anything. Yeah, so this is one key message of the whole course, of this whole course. A small training error does in general not imply good performance on new data points. You must always validate your model. And we will see now how we can validate a model. Yeah, a small training error just means or tells you nothing more in general than you were able to use this optimization or the fit function well. So if you get a small training error, this tells you the fit function works. And this might be non-trivial. So in some cases, it's non-trivial because you have to implement this fit function yourself. For deep neural networks, it's not so trivial to compute this fit function. But within this course, for basic models, this optimization or the training algorithms, they are so well developed that for sure you will get a small training error. So if you didn't make any trivial error, you will get a trivial implementation error. When you code the machine learning method in Python, you will get a small training error. So a small training error basically tells you you were able to use the machine learning library properly, but not more. Yeah, and you can see this, if you like, for the mathematicians among you. You can, for example, show that you can fit perfectly almost any, except pathological cases, any m data points using polynomials of degree n-1. As soon as this n is larger or equal than the sample size m. So let's consider the case of 2 data points where the polynomials of degree n-1 are straight lines. So if you give me 2 data points, I can always find a straight line that perfectly goes through these 2 data points. So this is one instance of overfitting. And in general, when you have many features, so when this n is large, n is also related to the number of features of a data point. So in modern applications, we have a lot of features. So if a data point is an individual person, then we have many, many features. We have travel history, we have healthcare records, we have genetic information, tons of features. And even a linear predictor with many features will overfit on a small training data or a small sample size. Okay, so how can we avoid overfitting? Well, the first step towards this is to detect overfitting. So how can we develop a method or a technique to find out that we overfit? There's one comment. How do we choose the most useful features? Yeah, so we will have around 6 on feature learning. There are a few useful methods that automatically determine the most useful features. these are called feature learning methods. And you can also check out scikit-learn feature learning methods. And you will find many, many functions for this. But we will have round 6 on this. Okay, so the basic idea, very important idea, maybe the key idea of this whole course, a very simple idea, but so important, and never forget to follow this. Divide the data points into 2 subsets. One subset we call training set. We use this training set to learn the predictor, to find the coefficients or the weights, for example, of a linear predictor or the coefficients of a polynomial predictor. And the other data, the other subset, we use to try out the predictor that we learned on the training set. And this is called the validation set. So let's look at one simple data set. So we have this data set of 4 data points. We choose one subset, these 3 data points here, is the training set. And the other subset, which only contains 1, but it's better than nothing, this is our validation set. And this data set we use as the training set. So with these data points, we do as we did up to now. So we fit a linear curve to these 3 data points. And after we fit this linear curve, so we use the linear curve then to predict the label of these data points in the validation set. So there's one question, what would be the best ratio of training set to the validation set? And unfortunately, there is no general widely applicable answer for this. So the best ratio depends on the statistical properties of the data that you have. And if you know the statistical distribution of the data set, then you can compute the optimal ratio of training to validation set. But if you don't know it, so you cannot do much than just try out different ratios and see how it works in the end. And by how it works in the end, I mean the validation error. Okay, so the principle is train on the training set. So we use these 3 data points to minimize the average squared error. So we choose the slope and the intercept for this linear curve in order to minimize the sum of the squared errors for these 3 error bars. After we have trained the model, we compute the validation error on this validation set. And then we get 2 numbers. We get the training error, which we obtain by optimizing the linear curve on this training set, and we get a validation error. But for the validation error, we didn't do any tuning. So this validation error is somewhat a truthful approximation or estimate of the generalization error or of the error that we get on a new data point. Okay, and we do the same with the other model. So we train on the training set. We choose the coefficients of the degree 3 polynomial based on these 3 points that we use for the training set. And then after we fit the polynomial to the training subset, we look how well does the polynomial predictor on the validation set. And here we see already this validation error is quite large. So this gives us already a hint that maybe the larger model, model 2, might not be good. And yeah, the basic idea of model selection is choose the model based on the validation error and not on the training error, because the training error always decreases for larger models. However, what is important is the validation error, because the validation error is a more reliable approximation of the general error that we expect on new data points. Okay, so and here we see the validation error for the degree 3 polynomials, which we call model 2, is larger. So we don't use this, but we rather go with the simple model. And this shows you one example where simple models, like a linear predictor, is preferable compared to more complex models. Okay, and then, yeah, there is a more fancy version of this validation, but the idea is the same. But instead of one split, because it might happen that this one split is a pathological case. So for some reason, this one validation set is not really representative. And in order to avoid bad luck in this split, we just repeat the split or the division into training set and validation set several times. let's say k times, and this is then called k-fold cross-validation. But the basic idea is, again, split into training set and validation set. But just repeat this split several times, and every time use some random mechanism to choose the training set and the validation set. Okay. Are there any questions up to this point? This was the meat of today's lecture. Model, validation, and selection. Okay, so then I briefly touch model regularization. So instead of, here's a question, we should ensure that the distribution of data in the training set and validation set is roughly the same. Yes, so this simple approach to validation only works if you randomly split into training set and validation set, and all data points can be modeled as realization of the same a random variable with one fixed probability distribution. This is sometimes called IID assumption. So IID, which means independent, identically distributed. So this is the fancy term for saying we assume that the data points are from the same distribution, so have the same statistical properties. And this might not be the case. There are then techniques that allow you to somehow test if the data points are from the same distribution or have similar statistical properties, but this is beyond the scope of this course. So, but we heard about one example where data points, a few data points are fundamentally different from the others. So they are not from the same distribution. Does anybody know how we call such data points, which are very different from the majority of data points? Outliers, yes, exactly. So one example where this is violated, this assumption does not work, is when you have outliers. So better be sure that you remove the outliers very early on. Okay. Yeah, model regularization. So far we used a somewhat discrete approach. So we had a set or a list of different models or hypothesis spaces. In the simplest case, two different. So model 1 was linear predictors, model 2 was degree 3 polynomials, but we could have any list of models or hypothesis spaces like decision trees, polynomials with different degrees, deep nets, and so on and so forth. And for each of these hypothesis spaces or models, we train and we validate. And then we choose the model which results in the smallest validation error. So this is the basic approach for model selection. A somewhat complementary approach is called regularization. And in regularization, we use one very large hypothesis space, like polynomials of very large degree 1,000, or deep neural network with billions of neurons. So in regularization, we use a very large hypothesis space, but in order to avoid overfitting, we use some structural properties that we expect from a predictor. For example, we could expect from a predictor not to change too fast. So we don't like to have predictors which change abrupt. So all of a sudden it reaches extremely large label values. So we would like to have the predictor change only slowly with features. Another example of structural properties could be symmetries. For example, when we develop a classifier of images that classifies an image into cat or no cat, then the predictor function should not change, or the result of the predictor map should be the same if we use a rotated image. because a rotated image of a cat is still a cat. And we can use the symmetry to rule out certain predictor functions, which are not symmetric. But you can find more on this in this YouTube video, which I have linked to here, where I talk more about this symmetries and also robustness. So this, what we require here is some robustness. So if the feature changes a bit, we do not want a predictor which changes a lot in the label, in the predicted label. Here's a comment that the change of predictor doesn't depend on the data. The predictor curve doesn't depend on data. Yeah, so I have shown here one particular predictor curve, which could be obtained by fitting it to these 2 data points. So we could have found this predictor curve because it goes almost perfectly through these 2 data points. But the other points here, they don't directly depend on these 2 data points, but we want to avoid such a function because it's not reasonable that it changes so fast. And how we can rule out such unreasonable function by adding a regularization term to the training error. So far, when we learn a predictor function, we try to minimize the training error. So this here is the training error, like the average squared error for a linear predictor or for a polynomial. But in order to regularize it, we want to punish or we want to penalize this training error if this predictor function edge is very crazy. So informally speaking, crazy, like it becomes very large, very fast. So then this craziness function would be a large number and the overall objective function would be large. So one example, if we use a linear predictor, could be, so if we use a linear predictor with a feature vector, so we use wi times xi, and one example that measures the craziness could be the sum of squared weights. So the sum of squared weights. And this could be a measure for the craziness of the function. So if the weights are small, then the function is not crazy. It's very slowly changing. But if the weights are very large, so then this function can change very quickly. And it's then a bit too crazy. So we would like to avoid this unreasonable or crazy predictor functions by adding a regularization term. So this is called a regularization term. And here, this is the training error. And often you will see this parameter lambda, which is a number, a numeric quantity, like non-negative. And this lambda chooses how strong we want to regularize or how much we want to avoid too fast or too quickly changing functions or too crazy functions. So if we choose this lambda very large, like 1 million, then we basically force the machine learning method to learn very flat curves. So the weights must be large. But if we choose this lambda very small, or in the extreme case 0, then this means no regularization. So we can fit any data and we allow for very crazy functions. So this lambda is called regularization parameter. But it can also have different names, or sometimes different symbols are used for this parameter. Where is it? Regularization. Parameter. Okay, yeah, that's basically about it. So to wrap up, today we have heard about the problem of overfitting. So modern machine learning models like deep neural networks or also linear predictors, where we use a lot of features, and this is the standard case in modern machine learning problems, because we measure so much about individuals. So we have many features about single data points. And when we use so powerful models, we tend to overfit. And the small training error does not mean much. It's always important and it's mandatory to look at the training, at the validation error, and moreover, to compare the training error with the validation error. When you compare those two, you can diagnose the method, and you can say, for example, well, it seems that I overfit the data. Maybe I need to get more training data points. So this comparison between training and validation error supports the diagnosis and development of machine learning methods. Okay, yeah, when you select models, do not use the training error, but always use a validation error for model selection. Yeah, there's one comment, is the parameter C in linear regression also regularization parameter? Yes, but I'm not sure if this C, there is one parameter C, and sometimes there's not a parameter here, but there's a parameter here, C, for example. But you can, instead of minimizing this function, you can also minimize the function by dividing through a constant like C. So you can cancel C here, and what you get is 1 over C here. So this C would have the role as the inverse regularization parameter. And what I said here about the value, the choice for the lambda, is then kind of swapped for C. So this would mean if C is large, this would correspond to no regularization, and if C is small, would correspond to strong regularization. So it's always important to look at how these parameters are defined. So how do the parameters show up in the optimization problem? But in principle, yes, C is a regularization parameter. It's related to regularization. Yes. Okay. Any other questions? Yeah, I will send out the link to a recording of this lecture and to the lecture on regularization, or to the more detailed lecture on regularization by my courses. You will get a link. Okay, thanks a lot. Have a nice evening and happy learning machine learning.